All right.
Okay, well, this is session 2B, I think, although it doesn't say that anywhere, but welcome to 2B. And I'm Rick Ansell, I'm the moderator, so blame me if I screw up. And our first speaker is Rima Chatterjee from the University of Cologne. And I turn it over to you.
Thank you. First of all, thanks to the organizers for giving me the opportunity to speak. And I will start with motivation, like why one should care about these knots in over-twisted contact manifolds. And for now, I'm not giving any definition of tight and over-twisted, but I'll just say that in three-dimensional contact geometry, there is this dichotomy, tight versus over-twisted contact structures. And if you look at the literature, you'll see that tight contact structures grab a lot of attention. People care a lot about them because of the classification, existence problem. Those are very difficult and interesting problems. So the natural question is why it seems like over-twisted contact structures are a little bit neglected. But the story actually is that Eliashberg's fundamental result, this is a result from 89, and that classifies over-twisted contact structure. So this says that over-twisted contact structures up to isotopy is same as a homotopy class of two-plane fields. So if one can understand this two-plane fields up to homotopy, they also understand over-twisted contact structures. So because of this classification result, people do not really work in over-twisted contact structure for a while. And it turned out the knot theory associated with over-twisted contact structures is actually very interesting and very mysterious. And in the last 10 years, people are starting working in this particular field and finding many interesting results. But it's still, there are a lot of gaps there. Okay, so now some background, because I was talking about contact structures but didn't give any definition. So here is the definition of a contact structure. So a contact structure on a three manifold is a nowhere integrable two-plane field. So this can also be defined as a kernel of a one form. And the nowhere integrability condition is basically the non-degeneracy of that one form. Intuitively, like nowhere integrable condition is telling us that we can never find a surface in the three manifold where the contact planes will be tangent everywhere. That means contact planes twist. That is the main thing okay, so, and there are two types of contact structures, tight and over-twisted. Like I mentioned before, there's this dichotomy. So if something is not over-twisted, that is tight. And an over-twisted contact structure is if there exists an over-twisted disk embedded in the manifold, and this embedded condition is very, very important. So if it's immersed, then that is not over-twisted. And definition of an over-twisted disk is this picture. So if you look at this two-plane field distribution, which is the contact planes, along the boundary of the disk, the planes are tangent. And this is the definition of an over-twisted. So if you start from the center of the disk and coming out radially, the planes are twisting, and that is actually taking a full twist radially. And so that's why it's over-twisted. And this picture is not due to me. I just copied it from somewhere, this nice picture. And here's an example of an over-twisted contact structure on R3. This is defined as a kernel of cosine r dz plus r sine r d theta. And because I'm not talking about tight contact structures at all, that's why I will not give like any example of tight contact structure. And as you can see in this picture, from the origin towards radially, the contact planes are twisting and again taking a full twist. So over-twisted contact structures means there will be a lot of twisting of the contact structure, which doesn't happen in tight manifold. Okay. Now knots. So there are two types of knots in a contact manifold, Legendrian and transverse. And the definition of Legendrian is take any point on the knot and the tangent vector to that point must lie on the contact plane. Or in other words, the Legendrian knot is a knot which will lie on the contact plane. And here's a local picture. For transverse, as you can guess, if you take the tangent vector to any point on the knot, that will be transverse to the contact plane. Okay. Now, classical invariants, these are used to determine that if the knots are same or not. And for Legendre knots, we have two classical invariants, Thurston-Banniquin number and rotation number. And right now, because I don't have enough time, so I will not define these invariants. And what I'll say that these invariants are well defined for null homologous knots. So we need a cipher surface to define these invariants. And for transverse knots, we have only one classical invariant, that is the self-linking number. Also, same, we need a cipher surface to define a self-linking number. But the definitions are pretty technical, so I'm not going into those. Now, how are Legendrian and transverse knots related? And this is a very important tool in contact geometry, or a technique in contact geometry, which actually allows us to move back and forth between Legendrian and transverse representative of the same knot type. So if we have a Legendrian knot, we can find its transverse push-off, and this operation is unique. So for every Legendrian knot, we'll find exactly one transverse push-off. Positive, when I mean, they're actually positive and negative transverse push-off, but when I am talking about transverse push-off, I mean positive one. And given a transverse knot, we can find a Legendrian approximation, but this one is non-unique. So for every transverse knot, we can find lots of Legendrian approximations, which is not really good. It's not unique, but there's a good news, and that is any two Legendrian approximations are related by negative stabilization, which is a local operation on a Legendrian knot. Okay. Now, knots in over-twisted manifolds. So how these knots are different. So basically, we have two types of knots in an over-twisted manifold. This does not happen in tight manifold. And why not? So in over-twisted manifold, we'll have at least one over-twisted disk embedded. In tight manifold, we have no over-twisted disk. Okay. So what happens if I have a knot in a manifold and I remove a tubular neighborhood of the knot from the manifold? In the complement, if I started with an over-twisted manifold, then the complement can either be tight or over-twisted. And how that can happen? So if the knot actually intersects every over-twisted disk, then if I remove the knot, I'm also getting rid of those over-twisted disks. So the manifold, the complement becomes tight. So these type of knots we'll call non-loose when the complement becomes tight. And if the complement is still over-twisted after removing the knot, then we'll call that loose. Okay. Now, what are known about these loose knots? Now, loose null homologous Legendrian and transverse knots are coarsely classified by Etnier. And here by coarse classification, I mean that contactomorphism, which takes one knot to the other. And again, contactomorphism is basically a diffeomorphism, which if I pull back the contact structure using that diffeomorphism, I get the other contact structure. Then we say that those two contact structures, like there is a contactomorphism between them. And coarsely classification, that means that that contactomorphism is isotopic to the identity. So it's a stronger one. And this result was also proved by Geiges and by Klukas independently. And there is another classification of Legendrian and transverse knots, and this one is actually a stronger classification. This is up to isotopy. Isotopy means either Legendrian isotopy or transverse isotopy. But here, notice there is one extra condition here, and that is telling us that there must exist an over-twisted disk disjoint from both of them. So we must have a common over-twisted disk, which actually is not required for Etnier's proof. So these two results are very independent, telling us about different things. So you might think that, okay, contactomorphism is a weaker classification, weaker notion of classification. But again, we don't have that common over-twisted disk there. And the second one is the classification is stronger, but then we need a stronger this thing that condition that over-twisted disk must be common. And this is due to Kahn and Chernoff. The second result is actually fairly recent. This is 2019. Okay. Now, what I proved is this is actually true for links as well. So it doesn't matter if we have more than one components, and if they are loose, that means if there is an overtwisted disjoint from the link, then we can coarsely classify them just by the TB and rotation number. So the classical invariants, they are enough to classify them. And here also one condition we need, and that is null homologous. We want every component to be null homologous. Otherwise, I cannot really define the TB and rotation number. So as a corollary, this is also true for transverse knots as well. So if we have, transverse links. So if we have two loose n component transverse links, again, null homologous, topological isotopic, and if the self-linking number are the same component wise, then they are coarsely equivalent. And these two, the proof is actually very technical, and this is heavily inspired by Etnayer's work. Okay. Now, next is open book decomposition, because I'm going to define an invariant for these links, both Legendre and transverse. And I'm going to use this tool, which is open book decomposition, very famous topological tool. So what is an open book decomposition? This is actually a pair with a fibered link and a fibration of the complement. So this definition is also known as the embedded open book. And there is another definition of open book, which is known as the abstract open book. This is defined by the fiber surface and a monodromy map using a mapping torus and then gluing them using the monodromy. But these two definitions are not really equivalent, because of course one is abstract, the other one is embedded. But we can go between these two definitions. So there are ways to go back and forth between them. And now contact structures and open books. So why open books? Why open books are so important in contact geometry? Before that, we say a contact structure is supported by an open book if these two technical conditions hold. So the first condition, if I do not want to go into these technicalities, what we want is the fibered link, which is the binding of the open book. We want it to be transverse, positively transverse, which is the second condition. And the first condition is telling us that if we take the tangent vector on the page of the open book, that appropriately approximates the contact structure. So vaguely speaking, these two conditions are telling us that. Okay. And given an open book, one can produce a compatible contact structure. This is an old result. Okay, so now why open books? Open books are important because the fundamental result of Giroux, which says that open book decompositions of a three manifold up to positive stabilization, again, this is a local operation on an open book, is same as contact structures on the three manifold up to isotopy. That means that we can find like lots of open books supporting one contact structures, but those open books must be related by positive stabilization. And this is a very important technique in contact geometry, because if someone wants to prove like something about contact structures, using this, they can move to this topological world of open book decomposition, prove something, and then push the result back to contact geometry. So this is very, very useful. Okay, so now we are ready to define the support genus of a Legendrian link, which is basically take the minimal genus of the page of the open book. So like I mentioned that one contact structure can be supported by lots of open books. So choose the one which has the minimal genus page. And then what we want the Legendrian link to be on the page of the open book. Now this is well defined because it's well known that every Legendrian link, we can put it on a page of an open book. That might not be the minimal genus, but we can always do it. And then just choose the minimum genus. That will be the support genus. Okay, so my next result is, suppose we have this coarse equivalence class of null homologous loose Legendrian link, then the support genus vanishes. So whenever we have a loose Legendrian link, which is also null homologous, we can always put it on a page which is planar. So That's nice. So one can ask that what about the converse? Can we say that if it's non-loose, then the support genus is always greater than 0? Turns out that's not the case. And there are examples of non-loose links with support genus 0. So here is one example. On the left hand side, the blue component and the red component. Also, I did not mention actually before that this is a contact surgery diagram of a non-loose link. Because we do not really have the front diagram in over-twisted S3. So here, just believe me that the blue component and the red component together, that is the positive Hopf link. And on the right hand side, we have the open book, the page of the open book, which supports this particular contact structure where the link lives. And we can put it on the page, the blue and the red one. And this is basically a disk with punctures. So this is planar. So non-loose, but still has a planar open book. So converse is not true. Okay. So what about transverse then? So like I mentioned, Legendrian link can always be put on a planar, not planar, on an open book. What about transverse? Can we always associate a transverse link with an open book? Well, if the transverse link is 5-word, then yes, sure. But if it's not 5-word, then what? So if we have any transverse link in any contact manifold, it be tight, over twisted, but we can always put this one in a sub-binding position, this transverse link. That means I can make the link a part of the binding of the open book, but not the binding, not the whole binding, because the link might not be 5-word. And again, using this theorem, I can define a support genus of a transverse link, which is similar definition: minimal genus, page of the open book, supports the contact structure such that T can be realized as a sub-binding of that open book. And so now we have two support genus, one for a transverse link and one for a Legendrian link. And actually they are the same. This is my next theorem. And this also gives a corollary to Unaran's result, where she proved that support genus of a knot is 0 when the knot is loose. So I extended actually her result from knots to links. And but she didn't say anything about transverse knots or transverse links. So using my theorem, I could prove, like, for transverse knots, null homologous loose knots, this is also true, that the support genus vanishes. Okay. Now, the question is, when does a non-loose Legendrian knot have a non-loose transverse push-up? Like I mentioned before, the support genus is not really useful in distinguishing loose or non-loose links. But it can be useful actually to find when a non-loose Legendrian knot have a non-loose transverse push-off. So basically, if we start with a Legendrian knot, which is non-loose, with support genus greater than 0, because non-loose can have support genus 0 as well, then its transverse push-off must be non-loose. This is actually not known. The other way around is known. If we start with a non-loose transverse and we apply Legendrian approximation, then it will be always non-loose. That is due to Etnayer. But the other way around is not always true. Okay. Now, last, I guess I have 1 minute. So just some future work. And that is this classification result for loose links up to Legendrian isotopy. Of course, this will be a stronger classification. And it turned out that it is actually, yes, we can do that. And this will be a joint work with Khan and Chernow. We are trying to extend their results. So they have this result for knots, and we are extending their results for links as well. But again, we have to have that extra condition that over-twisted disk must be common. Together, those two, like not having a common over-twisted disk and then classifying up to Legendrian isotopy, is very, very difficult. Like anything proving up to Legendrian isotopy is super hard. So this is one. And the second one is, what about the topological operation of a knot? So we have this connected sum, cabling, and Whitehead doubling. Connected sum actually does not preserve non-looseness. It's weird, but this is true, that if we take two non-loose knot and we do the connect sum, it's possible that we will get a loose knot. So what about cabling? And again, it seems like not always a cabling will preserve non-looseness. But then what conditions are required to preserve non-looseness? So this is a work in progress and joint with Etnayer, Min and Mukherjee, where we are trying to find conditions that where it seems like a TB, the Thurston-Bennequin number and the slope of the cabling, a relation between them will be the condition where it will preserve the non-looseness. But it's very weird actually that these topological operations are not really for tight contact structures. Actually, they are all true, but not for over-twisted. And I'll stop here. Thanks for your attention.
Let's thank Rima for talk. Very good. Are there questions that anyone would like to ask? I had some naive questions, if no one else wants to. So, first of all, if you have one of these over-twisted discs, does that mean it is of a very specific, is it, are they all isomorphic?
Yes, we can always arrange that all the discs are basically the same. There is a standard over twisted disc and we can arrange for them, but we don't really know that how many over twisted can be there, how the over twisted disc kind of like stay in the, maybe the open book for this is like a good question, that how the open book like the page of the open book intersects the over twisted disc. We don't know anything about those. Okay. But yes, the over twisted disc, we can think of them as like one type of over twisted disc.
Okay. Okay. And let's see. Oh yeah. So if you're in a contact manifold and you have a knot, is it of either Legendrian or what was the other category?
Transverse. Yes.
Yeah. Are they all? Is every knot isotropic to one or the other?
Yeah, every knot either is Legendrian or transverse.
Okay.
These are the only two types of knots.
Okay. And the third question was, in the open book decomposition, are the plane fields that you think about tangent to the pages of the open book? Is that how you're supposed to imagine the context structure?
It cannot be like cannot be tangents, but it can be like very close, like you can make them very close. The tangent vector will be lying in the like very approximates actually, but not everywhere tangent.
Okay. And so what then the binding is, how is it related to the plane field?
Oh, the binding is transverse to the plane field.
I see. Okay.
Always.
Okay, so I ran out of questions. And does anyone want to ask another question? Something more substantive, maybe? If not, let's thank Rima again for a very interesting talk.